Assalamualaikum. In this video, our group, I want to present my assessment MAT210. My topic is logic in board game and puzzle. This is the group members. There are four group members. Me, Muhammad Aminul bin Muazzam. The second members, Muhammad Nur Aziz bin Makno. The third members, Muhammad Afiq bin Akudin. The fourth members, Muhammad Shazwan bin Shazli. Now, we go into the first topic, is introduction. Logic is the key part of many board games and puzzles, helping players think careful, solve problems, and make smart decisions. Games like chess rely on logical thinking to plan move and find a solution. In this report, we will explore how different types of logic like statement and logical connective, turntable, and rules of inference are used in these games. By understanding this logical concept, players can improve the game strategy and also develop important thinking skills that are useful in every life. Now we go into the description of the concept. The concept that I will choose is a statement, a logical connective. A statement or proposition is clear declarative sentence which is either true or false statement. A statement can be a statement or not. A statement that has a truth value will be taken as a primary statement. The primary statement can be represented by a variable like x, y, p, q, and so on. Represented by a variable is called proportional variable. There are two boxes that show between statement or not statement. The example for statement is Kuala Lumpur is capital of Malaysia. The second example, 2 times 2 plus 3 equals 7. And then the not statement, for example, please come down plus, and next example, 2 times 8 negative 2 but not half equal. A statement shows the thing that want to be explained clearly whether it is wrong or right, while a not statement is a thing that is not explained and not clear, like a common sentence. And the next paragraph, few primary statements can be combined to form a single compound statement. It is the new statement formed by existing statement and logical operator. I want to show the logical operator. Number one is negation. The negation is logical non-operator. Do not as like a symbol to show the slide and negate the true value of a statement. This logic change a variable from true to false and false to true. And you can look the slide. They provide the P. P have the true and false. When the P true, change to false. When P false, change to true. And second, the logical operator is a conjunction. The conjunction is logical and operator. Do not as you can look at the slide what is symbol and connect to statement like P and Q and return the true only if both statements are true and false if either statement or variable is false. And you can look the table in slide. The example provide the P and Q, and there's the answer for the conjunction. And we are going to number 3 is a disjunction. The disjunction is a logical operator denoted as a V symbol connected to statement P or Q and return the true if at least one statement is true or both are true, and false if a both statement are false. And you can look the example at slide. You provide the P and Q and answer you can look. And next, the number 4 is implication. The implication is a logical if then operator known as a right arrow connected to statement if P then Q and return true if second statement are true or both are true or both are false, and false if the second statement is false. And again you can look the slide, provide the P and Q and show the answer for implication. And the last, the biconditional. The biconditional is the if and only if operator do not as a right and left arrow expresses logical equivalence. This means that P and Q must either both be true or both be false. You can look the example slide, provide the P and Q. And the answer for B equation Q.
Let me explain the concept of truth tables and why they are important in logic and reasoning. First, purpose of truth tables. Truth tables are important tools used to verify statement. They help us determine the validity of a compound statement by systematically analyzing all possible outcomes. How to construct a truth tables? When constructing a truth tables, we consider all possible assignments of true represent T and false represent F for each primary statement involved. This ensures we account for every logical scenario. Example of possibility. For instance, let's say we have three primary statements P, Q, and R. Since each of the statements can either be true or false, they are 2 power of 3 equal to a possible combination of those. This structured approach makes it easier to analyze and validate even the most complex logical statements. Now let's take a look at these two tables, which demonstrate how different logical operations work. In the basic setup, we start with the two primary statements P and Q. Each can either be true or false, and all possible combinations are shown in the table. Next, we have the negation column. This simply reverses the true value of a statement. For example, if P is true, not P becomes false. In the conjunction and column, the result is true only if both P and Q are true. Otherwise, it is false. For distinction, or the result is true if either one of the statements are true. This is only false when both P and Q are false. The implication if that column shows that the result is false only if P is true and Q is false. In all other cases, is true. Finally, the by condition. If and only if column indicate true if P and Q has the same truth value, both true or both false. This two tables provide clear representation of how logical operations are applied to statements. It is an important tool for analyzing and validating logical expressions. Now let's discuss the type of compound statement we encounter in two statements. First, tautology. Tautology is a statement that is always true, no matter what true values is variable to. For example, a logical statement like P or P not P is true in all cases. Second, contradiction. On the other hand, a contradiction is a statement that is always false, regardless of the true value of its variable. An example will be P and not P, which can never be true. Finally, a contingency is a statement that can sometimes be true and sometimes false, depending on the true value of its variable. For instance, P or Q will vary based on the value of P and Q. This classification, tautology, contradiction, and contingency are important for understanding and analyzing logical statements within truth tables.
Next, rules of inference. Rules of inference are logical tools used to derive conclusions from premises. It is formed the basis of logical reasoning, allowing us to construct arguments, prove theorems, and solve problems in mathematics, computer science, and philosophy. This can help build valid arguments and ensure that the conclusion follows logical from the information given. So next, we have tables of rules of inference. First, we have modus ponens. If P implies Q and P, then it becomes Q. And then we have modus tollens. If P implies Q and not Q, then it becomes not P. And then the third one, we have syllogism. If P implies Q and Q implies R, then it becomes P implies R. Then we have 4 disjunctive syllogism. If P and or Q and not P, then it becomes Q. And then we have addition. If P, then it becomes P or Q. Then we have the fifth one, we have simplification. If P and Q, it will become P. Then we have conjunctive for 6, and the rules of inference is if P and Q, then it will become P and Q. So then we have the seventh one, we have contradiction. If P leads to a contradiction, then not P. Then we have conditional proof. To prove P implies Q, assume P and derive Q. Then we have proof by cases. If P implies R and Q implies R, and P or Q, then it will become R. And then The ninth one, we have constructive dilemma. If P implies Q and R implies S and P or R, then it becomes Q or S. So the last one, we have destructive dilemma. If P implies Q and R implies S and not Q or not S, then it will become not P or not R. So next we have example of rules of inference. First, we have W implies X for premise 1 and X implies Y for premise 2, and 3 we have Y implies Z for premise 3 and not Z for premise 4. So first step, we can use syllogism for 1 and 2 and it become W implies Y, and then we can use modus tollens for 3 and 4 and it become not Y, and lastly we can use modus tollens again for 5 and 6 and it become not W.
Next, we will go to the application use. Next, we will go to the statement and logical connective example. As you can see at this slide, it have 5 different statements, and we need to identify it and convert it to 5 different variables, which is PQRST. It is to make it easy for the next step. Next, after the conversion of the statement into the variable, we also need to convert the statement into the logical operator. So the first logical operator we found is and also known as conjunction. So we convert it to the conjunction symbol, and then we go to the next sentence. It also have the conjunction word, which is while. So we need to convert it also. And for the next sentence, it has implication logical operator because it has if and then in the sentence. So we go to the next sentence, which is unless also known as or we can name it as disjunction. So we convert it to the disjunction symbol. And for the last step, we need to combine the all variable and the logical operator to make a final logical statement. That's all.
Next, we go to the next example, which is truth table. We need to construct a truth table for the following logical statements, which is P disjunction with Q and conjunction to not R and implies to P disjunction to not Q. Each variable is a different statement, which is for P, I attack the opponent's queens, Q, I protect my king, and R, I control the board. To construct a truth table, first we need to separate a logical statement into many parts, and then we list down the all original variable, which is PQR, and then we list down the true value and false value like the default format, and then we list down the variable that already changed by the logical operator, which is not Q and not R. Not Q Not is also known as negation. Negation is the opposite of the original statement. So for not Q, it is opposite of not Q. If Q is true, it will be false. But if Q is false, it will be true. The same goes to the not R. And then we list down the next statement, which is P disjunction Q. Disjunction is also known as OR. It will be false only if both statement is false. But if just one statement is false, then it will still be true. Next, we list down the next part of the statement, which is P disjunction not Q, and it is the same like the previous statement. So we go to the next part of the statement, which is not R implies to P disjunction not Q. Implies is also known as implication. It will be false only if the conclusion is false. The conclusion is the second part of the statement. Like in the question, the conclusion is the P disjunction not Q. So if just P disjunction not Q column is false, then it will be false. Other than that, it will be true. And for the last part, we list down the logical statement. The logical statement is connected by the logical operator. It is connected by conjunction. Conjunction is also known as AND. It will be true only if the both statement is true. But if just one statement is false, then it will be false. To conclude, the truth table can be determined their type by their
final logical statement value. If all value is true, then it will be tautology. If all value is false, it will be contradiction. But if it has a mixed value, which is true and false, then it will be contingency. So for this truth table, we can see it has mixed value, so it is the contingency. Next, we will go to the rules of inference example. From the questions, we can identify 4 different statements, and we can convert it to a variable PQRS to make it easy to implement it to the rules of inference. Next, we can read the sentence. Each sentence is a compound statement, so we can convert the compound statement to a variable that connected by the logical operator. As we can see, the first sentence we can convert it to the P implies Q. Next sentence we can convert it to Q implies R, and next sentence we can convert it to P disjunction S, and for the last sentence we can convert it to not S. After the conversions, we can implement the rules of inference to the question. Next, to answer the questions, the first step we need to do is to list down the 4 main statements in the table like in the slide, and then we can label it as premise 1, 2, 3, and 4. After that, we can identify which 2 statements can implement the rules of inference from the 4 main statements. I already identified it, and as we can see at the slide, the first we can use is disjunctive syllogism. We can use disjunctive syllogism to the statement 3 and 4. It is because it has a disjunctive logical operator, and it also have the almost the same variable, which is S and not S. So we can remove the S and not S, and we can get P. And P, we can make it as a new statement, which is statement 5. Next, we can use modus ponens to the statements 1 and 5. It is because it has it have implication logical operator. It also have the same variable, which is P, and then we can remove the P and left the Q, and then we can put Q to the new statement, which is statement 6. Next, we can use also a modus ponens to the statements 2 and 6. It has the same method as previous, which is it has a implication logical operator, and it also have the same variable, which is Q. So we can remove Q and left the R variable, and we can get the R variable as the new statement, and we can put it as the statement 7. So it already left the R, and we can use any rules of inference to the R because of R is the conclusion, which is if we can convert it to the sentence from the question, R is the I win the game. To know if our answer is true or not, we can see if all four statements is connected. For example, statement 3 and 4, we use rules of inference to them, and we can get new statement 5, and then we use rule of inference to statement 1 and 5, and it can be known as it is connected. And then we use rules of inference to statement 1 and 5 to become statement 6, and we use rules of inference to statement 2 and 6, and it's already connected. So with that, our answer is true. For the reference, you can go to the previous explanation slides. That's all from me, Muhammad Haji. After all of our explanation and examples, we can summarize that in board games like chess, it is important to use your logical thinking to analyze strategic positions to overcome your opponent move. The concept that we explained in previous slide, which is truth table and rules of inference, is also important in chess games. Implementation of this concept in chess game can improve your problem solving and critical thinking. It can make you to become a good chess player. To conclude, this concept not just being used for study in discrete mathematics, but it also can be used in real life too. That's all from our group. Thank you.